Okay, good morning, everyone. So remember last time we were talking about Newton form of interpolation polynomials, okay? So, well, we talk about Lagrange form, and Lagrange form, first you have to form the basis Lagrange polynomials, and then you form the interpolation polynomial like this. But then the drawback of this approach is every time you got a new point, then you have to compute the LJ again, okay? And then we talk about how to fix that. And then we talk about the Newton form. So the Newton form has the advantage that whenever you have a new point, then you don't have to recompute the previous coefficient, okay? And in order to do that, we have to define the divided coefficients. Okay, so the divided coefficient, I mean, it takes a bit lengthy to derive the formula, but once you have the formula, then you can compute them easily by a table. Okay, so you have a table of divided difference coefficients, and the table can be computed by, you just put in all the values here, x1, x2 up to xn, and then fx1 up to fxn, and then you compute the third columns by taking the difference in the in the second column divided by the first column, and then the third column you take the difference in the second column divided by the difference in the first column, but like a bit wider gap, okay, and so on. So that is the idea. And then we also talk about the errors. So now the errors. So this is just an example, yeah. So that remember the errors is the gap between the real function, okay, and the polynomial that interpolate the data. So remember, the interpolation allows you to have the function values equal the polynomials at the interpolation points only. Okay, so it means that the errors, equal 0 at the interpolation points, but at other points it might not be zeros. Okay, so this theorem will allow you to give more precisely what is the error function at any x. X is between like the lowest point x1 and the highest points. Okay, and before we give the theorem, we give the the statement of the theorem saying this. So the theorem says this: the errors. Okay, so we have to assume something. We have to assume that x1 is the smallest point and xn plus 1 is the largest point. Yeah, and we have to assume that the function is continuously differentiable of order n plus 1. So f prime, f double prime, the second derivative, f triple prime up to f of order n plus 1 primes, yeah, are continuous. And then once you have that condition, then there is this point xi. Okay, we don't know this point xi, but we know that we know that this point xi is in the interval between the smallest and the largest points. Okay, and then the errors can be defined like this. So it's derivative of order n plus 1 xi over n plus 1 factorials, and then the product of x minus all the interpolation points. And you can see that if you put in x equal x1, okay, then you just got 0. Or you put x equal x2, you got 0. Good question. Is it similar to Lagrange errors in Taylor series? Very good question. Actually, it is the case, but in Taylor series you have only 1 point, yeah, and you know, you can think in the Taylor series, everything collapse, you know, on the products now, like x minus x0 raised to the power of n plus 1. Okay, so somehow this is like the case when you have n plus 1 points. This distinctly different. But if on the points collapse, then you have the errors in the Taylor series. Exactly. This is a very good observation. Okay, so they are connected in some sense. Okay, so that's why before we prove this theorem, we have to prove a divided difference. Well, sorry, we have to prove the mean value theorem for divided difference. Yeah, and the mean value theorem. So last time I showed you that this theorem we prove is correct for, well, for 2 points. You remember 2 points is just a mean value theorem, right? And we prove it for 3 points. Yeah. And you know, for n points, you can prove the same techniques. So please read the lecture notes. I mean, the techniques will be the same. But now the whole theorem, this theorem will be used to prove this main theorem. Okay, the main, so theorem 13 will be used to prove theorem 12. Okay, so now how do we prove that? So you see, so there's 2 steps. The first step is the first step is we have to get the errors between f of x and Pn of x. So remember, Pn is the interpolation polynomial at x1 up to xn plus 1. Then it will equal, you know, this expression. Okay, so remember, this is a divided difference coefficient up to n plus 1 and the extra point x. Okay, and then you take the product of x minus xi, I from 1 to n plus 1. So this is a product of x minus x1 up to x minus xn plus 1. And then you just use the mean value theorem for divided difference to get out this coefficient. Okay, what is here? Okay, so the second step is obvious, right? Yeah. So now we just talk about the first step a little bit. The first step, how do we get these errors? Yeah. So maybe, so that is the main idea of the proof. So now go back to this very first step. How do I claim that fx minus pnx is just equal this? And now, so if you, so let me try to write out something. Now I will write on the whiteboard. So you see my whiteboard, yeah? You see, right? So now what I'm going to okay, so you can see it. So what I'm trying to show you that f of x minus Pn of x is going to be f, I mean the divided difference x1, x2 up to xn plus 1 x, and then the product of I to n plus 1 of x minus xi. Okay, so that is the claim. Okay, so maybe before we do this, let me take a very simple case. Let me take, say, just take just take 3 points. Yeah, so x1, x2, x3. Okay, so what does it mean here? It means that n just equal 2, right? Just a simple case. And then, so what is, in this case, then what is Pn? So Pn x will be you know, the Newton form will be f of x1, right? Plus f of, I mean, divided difference x1 comma x2, and then x minus x1, right? And then plus, so remember n equal 2, okay? So I just have Pn, actually just write P2, right? F of x1 comma x2 comma x3, x minus x1, x minus x2, yeah? And now, now suppose I have another point z, and now suppose I have, say, x1, x2, x3, and z, yeah? So I have to admit someone. So you can see that, right? So now remember, now we have an extra point z, yeah? So now then I have to increase the degree of a polynomial. So now I will take P3. Okay. So P3 now will equal, because remember before you have 3 points. So you use only quadratics, but now you have 4 points. You have to use a cubic. So the cubic will be f of x1 plus f of x1, x2, the divided difference over the first 2 points, x minus x1 plus f of x1, x2, x3, x minus x1, x minus x2, right? But now you have an extra term, okay? So now remember, because you have a point z here. So now the extra term will be f of x1, x2, x3, z, okay? And now you have a product of x minus x1, x minus x2 times x minus x3. Okay, so remember before we don't have this, because now we have an extra point. So we have this term. Okay, so then what if I take the difference? I take the difference, P3 x minus P2x. Okay, then it will be, okay, the whole thing, I mean the common terms, the whole common terms will go away. What you have left is just the last one. So f of x1, x2, x3, z, x minus x1, x minus x2, x minus x3, right? Okay. So far, so good, right? But remember that, you know, at so we still have the function f, right? So we assume that P3 interpolates f at the point x1, x2, x3, and z. Is that I'm talking about before? Yeah. This is exactly the case. You know, for the, suppose you have a new point, then you just compute the last term. Yes, that is another way to see it. Okay. Yeah, but what I'm trying to prove is I'm trying to prove this one. Yeah. So I'm trying to get it up to this. Yeah, but now see, because you have f minus Pn, right? And now I just take n to be 2. And I want to show that fx minus P2 will equal f of x1, x2, x3. Yeah. And then multiply with the product of all the xi here. Okay. So that's what I'm trying to do. Okay. So now go back to this one. So now what I'm trying to say that so we assume that P3 interpolates the function f, okay, as well at z. So we have f of z equal p3 of z, okay, because p3 interpolates f at z, okay. So that is our assumption. Yeah. So then I will replace this by f of z. Okay. So now I'm going to put in instead of p3 z, I will put f of z minus p2 of z. Okay. So f of z minus p2 of z, right? Now, if you rewrite this, then you see that now the equation will become x1, x2, x3, z, right? Nothing changed here. But now the x become the z. So z minus x1, z minus x2, z minus x3. Okay. So you see that it takes the form of this very first one, the very first line. Yeah. Right? Because now z is a dummy variables, right? Z is a dummy variable. So you can remove, I mean, you can relabel z by x. So then you get exactly the formula in the beginning. Okay, so this one is just we relabel z by x. Yeah. So you get the idea, right? So essentially, I just proved this very first line by, I mean, at least for the case n equal 2, by consider P2 and P3, right? And for the general case, you just consider Pn and Pn plus 1. Okay, then you can prove this equality. Okay, so this one is just the property of the Newton interpolation form. Okay, so you get the idea, right? So once you see it, when you see it for the case 3 points, well, 2 points is too simple, right? So the next step is only 3 points, and for 3 points, you see that this formula is correct. Yeah. So then, you know, if you apply it for Pn and Pn plus 1, then this formula is correct as well. So that is the whole point here. So now if I go back to the slide, so you see that we have f of x minus Pn of x equal this divided difference over x1 up to xn plus 1 and the extra point x multiply with the product of x minus xi. Now I run from 1 to n plus 1. Okay, so we got this equation. And then once we have this equation, we replace the very first term here, right? Using the mean value theorem for divided difference. And then you recover this theorem. Okay, so this theorem is very very useful. And somebody noticed, maybe James, and noticed that if all the points collapse into a single point, then you recover the errors of the Taylor polynomials, okay, of degree n. Yeah. So everything is related in mathematics. So now once you have this theorem, now suppose that I have an example how to use this theorem. Assume that I know a function f, okay, and I know that the derivative of order 3 is bounded by 3 in absolute value over the whole intervals from 0 to 2. So now we have 3 interpolation points, 0, 1, and 2, right? But we want to estimate the absolute errors at 1.5. Okay, so by P2. So we approximate F by P2 at 1.5, and we want to estimate the errors. And now, okay, so we don't have the work out here. So let me work it out on the piece of paper again. Okay, so you see my whiteboard, yeah? So I have to clear on the drawing. Yeah. Okay, so we have, remember we have the theorem, right? So we have the theorem. Now we have to apply the theorem for the case n equal 2, right? So now by the errors theorem, if you apply the errors theorem, right? So you just have E, so n, remember n here equal 2. So we just have E2, E2x is f of x minus P2, right? Then the theorem will give you, so you see my writing, yeah? So the theorem will give you E of x equal f to the third derivative, yeah, at some point xi over 2 plus 1 factorial and x minus x1, x minus x2, and x minus x3. Okay. So you see my writing, yeah? So now what is the next step? So remember, we want to estimate at x equal 1.5, right? So what is E2 at 1.5? Yeah. And maybe we just estimate using the absolute value. So we just take absolute value. Yeah. So then we have f to the third derivative xi over 3 factorials. So remember 3 factorial just equals 6, yeah. And this one you have 1.5 minus x1. So x1 is just equals 0. And absolute value, so we take absolute value for the whole thing. And then 1.5 minus x2 is just 1. And 1.5 minus x3 just equal 2. So some question. Does the errors formula works for both Lagrange form and Newton form? Very good question. So remember, the polynomial is unique. Yeah, P2 is unique. So the form, you know, it's just the way you write the polynomial. You can write in Lagrange form, you can write in Newton form, it doesn't matter. But the polynomial is the same when you expand it. Okay, so this P2 will work for both. So P2 here could be, you can write in Newton form, you can write Lagrange form, but it's still a polynomial. So remember, we have a theorem say that it's unique. Okay, so it has to work for both forms. Okay, so now, but it's very good observation, yeah. So now go back to this. Now remember, we have everything. Well, except that the derivatives, but we know that derivative, I mean, in absolute value will be less than or equal 3, right? So in the assumption, it will be less than or equal 3 over the whole interval. So you can make an upper bound and 3 over 6. And this one is just 1.5 times 0.5 times 0.5. Oh, sorry, the last one 0.5. And you know, you can multiply it out, you know, so I just leave it like this because I don't have a calculator here. Wow, I have, but you know, you just put in calculator and get out something. Okay, so 0.5 cube multiplied by 1.5 what is something. Okay, so dot dot dot, so it means that you have to put in the number here. Okay, so now that is a simple application of the theorem. So now we go back to the slide. So now you can see that now the whole theorem, you know, I mean, apart from the derivative, we don't know. But then the second part is this product. So it's very good to know what is the behavior of this product of x minus x1 up to x minus xn plus 1. Okay. And then, so that is the next topic here. So now suppose you have this function f is just 1 over 1 plus x squared, and you try to interpolate over equally spaced n plus 1 points over the interval minus 3 to 3. Okay, so now we just do some Lagrange interpolation, and you see that the function f, the blue curve, is the exact function, and then the polynomial is the green curve. And you can see that the errors could be very big, right? At interpolation point, it equals 0. But at different points, the errors could be big. The errors is the gap between the blue lines and the broken green lines. Yeah. And so this one, you have 5 points. So what is the degree of the polynomial? So if you have 5 points, then what is the degree of this polynomial? 4. Yes, very good. Yes. So degree 4. Yeah. So now if I increase the number of points to 15 points, this means that I increase the number of the degree. Yeah. Then polynomial is the blue broken line here. The green broken line is the polynomial. And the function is still a blue curve. And you can see that the errors are very good in the middle. Okay. But the errors is very big at the two ends. Yeah. And, you know, I mean, now we can explain that because if you look at this factor, phi x to be the product of, you know, x minus x1 up to x minus xn in the error function, then you can plot this error function, and you see that the errors, I mean the factor phi x in the errors function, yeah, is very close to 0 in the middle points, but it becomes huge, right? This is like 10,000 at the two ends, from minus 3 to 3. So how do we fix the situation? How do we fix the situation? So this one is just explanation, right? How the errors got big at the two ends, right? Because the consequence of this factor phi and the consequence of the errors function. So it got multiplied by 10,000 when it get close to the two ends. So how do we fix the situation? So how do we fix the situation? So what is the way to fix the situation? Or you can make some guess. Well, I mean, increasing the degree of polynomials. Well, okay, I don't know, but just make some guess. I mean, increase the degree of polynomial doesn't help because it just make it bigger, right? But make some guess. How do we fix the situation? More interpolation point. Yes, very good. More interpolation point, but where? Cut off the end. Well, you can cut off the ends, but then it's like you modify the function. Now the function are given. But yes, so you see more points at the end. Yes, more points at the end. Exactly. So more points at the end. And you are not the first one. Okay. So Chebyshev, I think he's a Russian mathematician in the 19th century. He solved the problem. So by putting more points at the end. Okay. And the way he did it is he just plotted a circle, not a circle, but a semicircle. Right. So remember, before you divide the interval into equally spaced points. Yeah. But he divide the semicircle into equal arcs, equal arc length, right? So you see, you see the pictures, and then you project on the points on the semicircle back to the intervals, and you see the effect is you have more points at the ends, on the two ends. You mean slick method, right? Not slick method, slick method. Yeah. So then you know, I mean, when you see the pictures, you can write down the formula. Okay, so the formula. Okay, it's a new word. You can write out the formula. Okay, so once you see the pictures, you can write out the formula. You know, I mean, for any interval a and b, yeah, you can write out the formula for xj like this. And you see, because Chebyshev, he came up with the formula, so now people have to call this a Chebyshev points. So if you have some new set of points, people can name after you, say after 200 years. Okay. So then, if you use Chebyshev points, then the errors are reduced at the two ends. You can see that. Okay, so the errors before, you know, very big at the two ends, but now it's very small at the two ends. And now, if you use Chebyshev points, then you can see that for 4 points, we have this situation. But for 15 points, 15 Chebyshev points, the polynomial agree very well with the function. Okay, so that is the advantage of Chebyshev points. You put more points at the two ends. Okay, and this one is just like you plot the errors, right? So the plot the errors, and for n equal 10, the errors is about 3/10 to the minus 2. But for n is 100, you get down to machine errors. Okay, so, and then this one is just a MATLAB script, how you interpolate the function over the equally spaced points. Okay, so here I use a polyfit, but you can use Lagrange form or Newton form. So, and so you saw the command line space already. Okay, and now this one just a plot. And then, so evaluate the function phi. Well, you can compute this one. Well, if you compute this one over many point x, then there's a command repmat, replicate the matrix. Very handy. Okay, so you just look it up. Okay, and then you take the product, and then it gives you the function phi. So here x could be like a collection of points. Yeah. And so then it's easy for you to plot, and x data are given as a vector. And so this one is another function for given the Chebyshev points. So this one, we just apply the formula. Okay, so we just translate the formula into MATLAB. Okay, so pi in MATLAB is just written like this. Okay, so now maybe we have enough with interpolation already, but you can ask yourself that, you know, sometimes life is not easy, right? You cannot fit the data exactly. Yeah. So suppose like you look at the stock market, you know, it go up and down every day. You know, suppose you're playing with the stock market, then it's go up and down every day, and you cannot connect, you know, on the dots with a simple polynomial, right? And then now they come up with the least square approximation. So the least square approximation is, so suppose you have a collection of data, okay, TIYJ for m points, okay. Then we try to find the line, that minimize the square of the residual, okay. So the residual is just the difference between, see, this is the point on the line, yeah, and this is the data point. So maybe let me draw pictures. It's easier to explain by pictures. So now you have, so suppose I have so you can see my drawing, yeah. So suppose I have this one is T1. T1 is that time 1, okay, like day 1, day 2, day 3, and so on up to TM, right? And then here you have Y1, okay, here you have Y2 and Y3 and so on. So this one is YM. And you can see that you cannot have a line that fit through M points, right? Because a line that go through only 2 points, yeah. But at least you can have a line that somehow minimize the residual. So what is the residual? So suppose, so this is a line alpha plus beta t, right? So this one is say y, yeah. Well, y here is different from y1, y2, right? I mean y just a variable. Okay, so then so the residual is this distance, right? So this distance and this distance. Okay, so what is the red point here? So the red point here is just T1, well, not T1, but beta T1 plus alpha, right? So the red point here, yeah. And then the blue point is just Y1, yeah. So then this one gives me the first residual. Okay, so this one is R1, yeah. And then similarly you have R2, R3, Rm, okay. But residual could be positive, could be negative, yeah. So you have to sum up on the square, otherwise it could be, like positive, negative. So you have to sum up Tj plus alpha minus Yj square, right? And you try to minimize it. You try to find a line that minimize this sum of squares of the residuals. And we call it the lines of best fit, okay? So how do we do that? So how do we find the line? So, you can write down as, so I show you the calculation here, yeah. So you can write down, so the residual is here, yeah. So Rj just alpha plus beta Tj minus Yj, you saw it. And we minimize the Rj square. And before we do it, we can write down in terms of a matrix A. Okay, the matrix A is like coefficient matrix, 1 T1, 1 T2, and 1 Tm, and multiply by x. So x is the unknown coefficient alpha and beta of the line, yeah. And then, A multiplied by x okay, minus y will give you the vector of the residual. Okay, so you can check this. And then the least square problem is you try to minimize this function, capital F. Yeah. And you see this could be written like this. And if you remember your calculus in first year, right? When you have two variables, then in order to find minimum, you have to set the partial derivative with respect to two variables equals 0. So for one variable, you just set the derivative with respect to that variable equals 0. But here you have two variables. Okay. And if you set partial f with respect to alpha equals 0 and partial f with respect to beta equals 0, then you just have two equations. Okay, so two equations in alpha and beta, and you can solve for this. Okay, so for I think there should be a number 1 here. So there should be a number 1 here. I can fix the slide here. So alpha sum of 1, yeah. And then, you know, once you solve it, then you get alpha and beta. And another way to look at this is you can write F as this product R transpose R, right? Because remember, F is just the two norm of a vector, right? So two normal vectors you can write out like this, yeah. And by the definition of the residual, you plug it in, yeah. So the residual Rx minus Y, you plug it in here and you expand it, okay. Then you can set the partial F with respect to alpha, partial F with respect to alpha beta equals 0. You obtain this equation, normal equations. Okay, so look, this one, you know, you have to do some calculation. Okay, when you take partial with respect to alpha. So remember this one, there's a collection of x squared, right? So when you take the derivative, it becomes 2x. So eventually it will come down like this. And this one, you know, I mean, this is a collection of x, right? When you take derivative, the x goes away, and you have 2x, and 2 got canceled. You got these normal equations, yeah. And then, you know, I mean, you can verify that either approach give you the same solution. Okay, so but at least this approach, it look like you can put in MATLAB easily, right? This approach, well, you have to know the matrix, but then after that you can plug in the MATLAB to solve this system. Okay, and here just a 2x2 linear system, so we can solve it by any methods. Okay, and in this case, you know, you got the same linear system here, so M here. So again, I have to collect. I have to correct the typos here. So there's a missing terms. Okay, so the missing term is sum of dj. Yeah. Okay, so now once you have it, you solve it, and you get alpha and beta. So look for example. So suppose I have ti, I from 1 to 5, okay, is 0, 0.5, 1, 1.5, and 2. Then yj is given like this. Then I define the vector t, and I define the vector y. Okay, so I just put this data into the vector form, and then I form the matrix. So remember the matrix, the coefficient matrix. It's just ones in the first columns, and then T1 up to Tm in the second column. So this one is the command that gives you the matrix. And then, okay, so now MATLAB, the backslash command. Okay, so when it sees the rectangular matrix, then it knows that it has to solve a least square problem. So backslash, when it sees a square matrix, just do the Gaussian elimination. But when you see the rectangular matrix, that inside this command, it will solve this normal equations. Okay, we don't have to give this normal equation for MATLAB. MATLAB just understood. Okay, just understood. And then if you put it in MATLAB, then you get, this is alpha and this is beta. So the line is given by this formula. Okay, and you can plot it. So you plot it. So you plot it by given many points t, yeah, from 0 to 2, and this is the lines that best fit the data, and you plot, the lines are blue line, and the data is just a marker, magenta with a star, and this is what is going on. So you see the data is a magenta star, and the lines of best fit is just the blue line. Okay. So any question? So far so good. On good. Okay, it's good. Okay, so now what happens if I don't use the line, but I use the quadratic? Okay, so then we have a quadratic of best fit. So remember here, then you carry out the same process, yeah? So you got the quadratic to be defined to be alpha plus beta t plus gamma t square. So alpha, beta, and gamma are unknown, right? So we try to find the quadratics that best fit to the data in the previous example. So again, we define the residual. So residual is the points. Well, first, this is residual vectors. So you take the points on the quadratics, okay, minus the data points. So minus the data. And then this is the last data point. You take the quadratics, you apply to that last data point, you minus ym. And then, so now the coefficient matrix in this case will be this matrix. So why is that? Okay, so this one, let me write down a bit more explicitly why we got the coefficient matrix like this. So now you have, so let me clear this. So you have a, so remember the residual, okay, is a vector, alpha plus beta t1 plus gamma t1 square minus y1, right? Dot, alpha plus beta tm plus gamma tm square minus ym transpose. Okay, so this one is transpose, yeah. Then the residual is defined to be ax minus y. Okay, so now what is x? So remember, x will be a vector of 3 unknown coefficient, alpha, beta, and gamma. Yeah. So now if you write down this residual, yeah, it will be something like, well, alpha plus beta t1. Well, I just take the residual again, yeah, but I write down in the form that easier to see, right? So t1 up to alpha plus beta tm plus gamma tm square minus vector y1, y2 up to ym, right? So you split it into two vectors like this. But the first vectors can be, now if you put in the alpha, beta, and gamma, yeah, then, so this one will be 1 and then t1 then T1 square. Okay, so you can see that 1 T2 square and so on up to the last one, Tm square. So this is the coefficient matrix minus y1, y2, ym dot dot. Okay, so this is the matrix A. So this is the matrix A, and this is a vector X, it's a vector Y, and this one just a matrix A. Okay, so that is how I got the coefficient matrix. I rewrite the residual vectors. And now, you know, remember we just need to define the residual. Well, we just need to define the coefficient matrix. So then you put in MATLAB. Okay, so this is the coefficient matrix. Yeah. So once in the first column, and then T1 up to Tm in the second column, and T1 square up to Tm square in the third column. Yeah. And then you get you solve the least square. Okay, so backslash here just gives you the least square solution. And then you plot it. So the solution gives you like this. So we just take it out from MATLAB, and you see the curve, the blue curve, okay, is the quadratic that somehow fit the data in the least square sense. Yeah. So in general, you can use any polynomial of degree n less than m. So why n has to be less than m? So why n has to be less than m? Strictly less than m. So remember, you know, when you, yeah, because otherwise you have, you see, when n is exactly m minus 1, then you have interpolation, right? But when n equal m, then you have ambiguous solution. Yes. Another way to say that, you know, you have infinite many solutions. Yes. So that's why you have to assume that n is strictly less than m. Okay. And the special case when n equal m minus 1, then you just have the square matrix that give you interpolation. Okay. So then you can define the residual vectors, you know, like we did before. Before we just has a line and then the quadratic. But in general, you can, when m equal n plus 1, then you have interpolation. Remember? Interpolation, you have the degree exactly 1 less than the number of points. Yeah. So when m equal n plus 1, then you just have interpolation. We studied interpolation already. Okay. Well, I mean, just forget about the n and the m. Just take the number of points. Okay. Then if you minus 1 equal the degree, then it's interpolation. Yeah. So then, you know, n equal m minus 1. Okay. But if you say m equal n plus 1, yeah, then it's still the same. You know, you have one more extra point more than the degree of interpolation. You know, degree interpolation is n, then m is n plus 1. Okay, it's the same as you have m points and n equal m minus 1. Okay. So anyway, so now we go back to this. Yeah. So this general case. Yeah. Then the residual vectors is given by this. You know, the like you saw it before. You know, the points you evaluate by the polynomials, and then you minus the data. Then the residual, okay, is given by the vector r equal ax minus y. And now the coefficient matrix is given by this. The first column is just ones, yeah. Second column is t1 up to tm, and the last column is just t1 up to, t1 to power n to tm to the power n. Okay, so we take the square of r, try to minimize those. It's very good point, very good point. If you just take absolute r and minimize the sum, then this theory doesn't work anymore. Okay, so if you take, it's very good observation. If you take only absolute r, then you got a different problem. You don't have a least square problem. Yeah, you have a minimized, but in what they say in the L1 norm, and the whole techniques here doesn't apply. Okay, so it's different. You can have a different solution. Well, this definition is accepted as a least square solution when you have a different norm, the one norm or infinity norm, and they call it with a different name. They don't call it least square problem anymore. They call it like minimize L1 norm problem or minimize L infinity norm problem. And then we have to give the whole set of lectures with a different techniques. Okay, but people did that. You know, because in image processing, you know, sometimes the two norm doesn't give you the good solution. It just blur out the features. And you know, people say that why don't we use the L1 norm or L infinity norm, and it improves, okay, the solution. But then you have to use different solution. Okay, so different techniques. But yes, it's very good observation. Yeah. But then we don't have time to cover it here. So in this course we just cover everything, but with only in the introduction level. You can go further. Okay, if you take maybe third year, fourth year, or master degree or something, or PhD. Yeah. So then, you know, you can use the same techniques and you take partial derivative, and then you solve normal equations. You know, by the same techniques, then you solve the normal equation like this. Okay. And in MATLAB solve a normal equation for you. And I think we don't have time to go to another case, but at least, you know, you can do it in MATLAB with any derivatives. Any polynomials. Okay. So I think we should stop here. So I will stop the recording and see whether you have any question.